Welcome to the second homework of the machine learning, and let me open the files. The files was this one for the second week, and this is there's the example data in here, and there's some exam images to display it, and this is the public test Python file, and this is the test utilities, and this is the utility files. Uh, in this homework, we are doing logistic regression. In this exercise, you will implement logistic regression and apply it to different datasets. And these are the outlines. And first of all, we are running the cells to import the packages, NumPy, Matplotlib, and utils.python. And utils.python is this one. It's also using NumPy and Matplotlib. We will check it later on. Okay, let me come here and let me run this one. Okay, it's changing. Yeah, I was using base Python, I guess, for the last homework, if I'm not remembering wrong. Yeah, let me run it. Okay, it has been run. It just and the second logistic regression. In this part of the exercise, we will build a logistic regression model to predict whether a student gets admitted into a university. And the first one of it, problem statement. Suppose that you are an administrator of a university department and you want to determine each applicant's chance of admission based on their result on two exams. You have historical data from previous applicants that you can use as training set for logistic regression. And for each training example, you have two application scores and two exams and admission decision. You task to build a classification model that estimates an applicant probability of admission based on scores from those two exams. And in 2.2, loading and visualization data. And we'll start loading the dataset for this task. The load dataset function just below into variables xtrain and utrain. And xtrain contains exam scores onto exams for a student. And utrain is a admission decision. And you train 1 if the student has admitted, and you train 0 if the student was not admitted. Both at X and U train are NumPy arrays. Probably they are in here or here. We have to check it. And this is losing the test. Let me do it. Print X train. Let me run this one. Actually, it might be. Yeah, actually, it's typing here. The X is starting is 44. Yeah, this is the X values in here. Isn't it? Yes. And let me check the U train. Let me run it. And U train 000 and ones goes like ones. Not this one. No, actually, this is one. I guess it's just rounded. Yeah, it is here 111 and zeros. Probably trains. Let me delete it. Let me run back. Okay. We have the variables. In 5 element X is here, as we checked in here, the previous one. And probably it's given the U for the 5 of them. And it's in here. The type is NumPy arrays. And check the dimension of your variables. Another useful way to get familiar with your Schramm data is dimension is print the shape of X and U. So it's given the shape for us. There are 100 examples. And this is the visualization. Before starting to implement any learning algorithm, it's always good to visualize the data if possible. The code below displays on the data 2D pilot, and where the x's are two exam scores, and the positive and negative examples are shown with different markers. And we use a helper function in the utils.python to generate the Python. Yeah, let me check the helper function in utils. Oh, helper. Actually, did I write? Did I make it wrong? Help. Okay. It's given the pilots, but I just wanna try to make it use a helper function. I'm just trying to find the helper function from the utils, but I couldn't find. Let me read this code. So I just given admitted and not admitted examples. These are not using any pilot, but maybe pilot data might be in here. Yeah, it is here. Pilot data, and this is the definition. We have x, u, and post label u equal 1, and negative label probably u equals 0. So positive equal to u, and that's equal to 1. And negative equal to u when u becomes 0. And we are just displaying in here, as we can see in here. And the goal is build a logistic regression model to fit this data. With this model, you can then predict if a new student will be admitted based on their scores on the two exams. And there's some sigmoid function which is given in here. To recall that logistic regression, the model is represented as where the function g is sigmoid function. The sigmoid function is defined as let's implement the sigmoid function first so it can be used by the rest of the assignment. And this is the exercise one. Complete the sigmoid function to calculate, and there's a note for it. Z is not always a single number, but it can also be an array of numbers. If the input is an array of numbers, we'd like to apply the sigmoid function to each value in the input array. So if you get stuck, you can check the hints. When you're finished, try testing a few values by calling sigmoid x. In the cell below, the larger positive values of x, the sigmoid should be closer to 1, while the larger negative values of sigmoid should be close to 0. Evaluating sigmoid 0 should give the exactly 0.5. And it's given error because I haven't run it. Yeah. And NumPy has function called numpy.x, which offers a convenient way to calculate the exponential e over z of the all elements in the input array z. Click for more hints. I'm just clicking here, actually. Yeah. And details are here. And input 3, numpad exe, details, font size. You can translate code as numpad xd. You can translate code as this one. So if you are still stuck, you can check the hints represented below the function figure out to calculate g. Okay. End of the details, summary, font size 2, dark bluish, and yeah, okay, this is just given the how it is looking like. And yeah, in here we are given sigmoid, isn't it? Yeah. And expect output is sigmoid 0 is equal to 0.5. So I will stop in here to find the solution. After I find it, I will restart the video and we'll try to explain the other things. So let's continue to writing the code part in here. We have to write g equal because it's returning to g, and g equal 1 divided 1 plus exponential, isn't it? No, I'm sorry, numpy dot x and minus c, but it comes here, so some divisions. It must be like this one. Let me run it, and let me run it. It gives 0.5 as we expected, and I'm running this one, and this is 32 also. So cost function for the logistic regression. In this section, you'll implement the cost function for logistic regression, and this is the example 2, and it gives our examples. And there's a gradient for logistic. Okay, how many? Okay, let's continue. In the example 2, implement the cost function for logistic regression, and this is the exercise 2. Complete the compute cost function using the equation below. And recall that for logistic regression, the cost function is of the form, which is here, where m is the number of training examples in the data set, and is the cost single data point, which is the given formula in here. So model's prediction value over, which is actually labeled, and g is the sigmoid function. It might help for calculating an intermediate variable. Note, as you're doing this, remember that variable x train and u train are not scalar values by matrices the shape of mn and m1 respectively, where n is the number of features and m is the number of training examples. Can use sigmoid function that you implement below this part. And okay, let me click the hints. Okay, it gives some details for me. And okay, the total cost. Does this give the whole thing? Okay, I will just continue to reading the other stuffs, and I will stop and fixing everything, and I will come back. And after this example, we're gonna go to gradient for logistic regression. And okay, let me solve the whole problems till the end, and I will continue from the exercise 2. Okay, we've already in the second of it, and we have to calculate this one. This is comes like this one. Okay, we have to calculate the cost. So we are starting with z, and which I defined in here, and this is the dot function. So we x and v. So in here there's x and v, and we plus b. So the z tilde here for here, and it gives us this one. We are using the dot function, and it's just in here, and we're given it as a name as prediction, and it's a sigmoid function z. So to calculate the cost to do this, we're just using, where is it? We are using this function, and which is in, where is it? And is a sigmoid function, which is this one. So, and we're calculating total cost. Let me run it. It might be wrong. I'm not sure about my code. You have to see it. Yeah, okay, it's true. I take some help in this code because I couldn't be sure of it. And in here, gradient for logistic regression. They're just simply functions, and I don't want to make it too long for my homework. So I will not read this ones, but I will try to explain my code. So in here, in the section implement gradient for logistic regression, recall the gradient descent algorithm is this one. So in here we are coming again the z, and this is the dot function. So we are using x and w plus b, and which is in, where is it? Yeah, which is in here. Which is in here. So, and we are actually just implementing the function, the mathematical notations in here. And the EDVB is in here, 23, and it's in the here 1 divided by m, and summation function in here, as you can see, summation notation, and we are calculating it. Actually, this is given in here, so let me run it. Yeah, this time basically calculus, and let's run it. Is it true? 0.1? Yeah, it looks true. And using learning patterns using gradient descent, similar to previous assignment, you will not find the optimal parameters of a logistic regression by model by using gradient descent. You don't need to implement any for this part. You simply run the cells. Okay, let me run the cell. A good way to verify the gradient descent is working correctly, GBP and decreasing. And let me run it. Yeah, and let me run this one too. Yes, okay. And in here, uh, there are many derivatives and there are some explanations of it. And we are taking J and V histories and using this one for the iterations. And there are the here for calculating the cost for each of them. And we are plotting a descent boundary for this one as admitted and not admitted. And this is now our output within the matplotlib with bitpilot. And it looks actually the same. And to evaluate in the logistic regression, we can evaluate the quality of parameters we have found by seeing how well the learned model predict in our training set. You will implement the predict function below to do this. Please complete the predict function to produce 1 or 0 prediction given dataset and a learned pattern vector W and B. First, you need to complete the prediction from the model function x power I and g v dot x power I for every example. And these are the functions. So we are doing comment to here, and we are have to calculate the z. I use z and bb plus. I think so. This is where again? Why I cannot see now. Yeah, anyway, and prediction sigma z as this one, and for this one, this is the prediction. So if it is the p bigger than this one, we are using 1 or zeros. And when we are running this one, this comes true because simple functions is the dialog same as we done it before. Actually, probably I wrote this code before this one, and this is calculating the predictions and regularized logistic regression. And in this part of the exercise, you will implement regularized logistic regression to predict whether microscopic from a fabrication plant basis quality assurance QA during QA. Each microchip goes through the various tasks to ensure its function correctly. And the problem statement, suppose you're a product manager of the factory and you have the test results for some microchips on two different tests. From these two tests, you would like to determine whether the microchips should be accepted or rejected. To help you make the decision, you have a dataset of test results on past microchip, from which you can build a logistic regression model. And let me run this one. This is the loading the training sets, and for this one, the displaying and the check dimension of the variables. Let's run it. And this is our variables, which is 188 variables. And let me run this one, and we're seeing is it like this one. These are some rejected and accepted. It's not looking logical, so we have to make some feature mapping on it. So there are metrics, and to display it, let's run this one. Here we have to make the mapping for. We cannot understand. There's nothing like this one, so we cannot take it as the good data set for us. There are another good outliners or liners. All of them look like the outline. One way to fit the data better is to create more features from each data point. In the provided function map feature, we will map the features into all polynomial terms, like kind of matrices. And we just run this one, and we are calculating the cost function in here. And or another exercise is computing the cost function. This is lambda divided by 2m and summation with j over power 2 and g. And if you come here, this is the for the regression function. We are first taking the square root of it, which is this part. And for the total cost, we are having the regression cost is multiplying this one, and we have lambda divided by 2m, and which is this part. We have to adding the cost without the regression. So it is in the here, and we're turning into the total cost. So we are calculating just a regression in here. And the below implementation, let me run this one. Let me run this one. Oh, okay, we have an error because I forgot to run this one. Yeah, has been run, so I can run this one, and we're taking the good output. For here, yeah, gradient for regularization logistic regression. In this section, you will implement the gradient for regularized logistic regression. The gradient of the regularized cost function has the component, and this is here, and this is the scalar. And let's come here, and again, just a mathematical formulation. I don't want to read all of them. And completing the complete gradient regression function below the method, and the start code terms gradient compute. Yeah, actually what we have done, I'm not even remembering this one. Yeah, okay, this is dj equal lambda m divided 1, and we are must be given lambda in here, so it is equal 1 divided m and times v, and it is taken the x, u, v, and b, so this part in here. And let me run this one. These are looks true. And learning parametric using gradient descent and optimization parameters VB. And if you have completed the cost and gradient for regularized logistic regression correctly, you should be able to throw the step next cell to learn the patterns V. After training our patterns, we will use it to plot the decision boundary. And this is here, and it's just making iterations 1,000 times and plotting the decision binaries, but it's not a good example. And taken like this one, but it looks actually awkward. The boundaries taken with the decision boundaries with u equals rand d equal 1s, and after learning the parameters VB, the next step is plot decision boundaries similar to figure 4, which is given here. And within this evaluation, as we can see in here, this is the 80%, because in this boundaries we have should taken some things in accepted way, should be rejected, and there's some accepted should be rejected. And thanks for the listening. day. Have a good day.